topic is matrix chain multiplication. First, I will explain multiplying two matrices A and B. We can multiply two matrices when they are compatible. Compatible means the number of columns of A is equal to the number of rows of B, like this. This is a 2 by 3 matrix, and this is 3 by 2 matrix. So the column number is the same as the row number. Then we can multiply these two matrices. So, and if A is a P by Q matrix and B is a Q by R matrix, then the resulting matrix is P by R matrix. And another. The number of scalar multiplications to multiply A and B is PQR. Why? Because we have to compute PR elements in the resulting matrix. So, PR elements. And to compute an element in the resulting matrix, we have to multiply, we need Q multiplications. So, the total number of scalar multiplications is PQR. Then I will explain the order of matrix multiplications. The order of multiplications does not change the value of the product because the matrix multiplication is associated. For example, the result of the left-hand side is the same as that of the right-hand side, and we all know it. But the order of multiplication affects the number of scalar multiplications. Look at this example. We are going to compute the product of the three matrices, A1, A2, and A3. And A1 is 10 by 100. A2 is 100 by 5, and A3 is 5 by 50. Then we have two choices. We either multiply A1 and A2 first, or multiply A2 and A3 first. Let's count the number of scalar multiplications of both. If we multiply A1 and A2 first, then we need PQR, that is 10 times 100 times 5 multiplications. It is 5,000. And the resulting matrix of the product of A and B is 10 by 5. So we have to multiply a 10 by 5 matrix and 5 by 50 matrix. Then the number of multiplications is 10 times 5 times 50, which is 55,000. So in total, it is 7,500 scalar multiplications. Then the next one. First, we multiply A2 and A3. It takes 100 times 5 times 50, which is 25,000. And the resulting matrix is 100 by 50. So the number of scalar multiplications in this case is 10 times 100 times 50, which is 50,000. So in total, it takes 75,000 scalar multiplications. Then let's compare these two cases. If we multiply A1 and A2 first, then it's faster by 10 times. 10 times faster. So we have to consider the order of matrix multiplications. Okay, now let me define the matrix chain multiplication problem formally. We are going to multiply n matrices from A1 through An. And the dimension of A1 is P0 by P1. And the dimension of A2 is P1 by P2. Similarly, the dimension of An is Pn-1 by Pn. Usually, we use this notation, P1 by Q1, P2 by Q2, and Pn by Qn. It is normal, but in this case, note that the column number of A1 is the same as the row number of A2. So we can save the notations like this. P0 by P1, P1 by P2. So generally, AI is Pi minus 1 by Pi. Then the question is, find a full parenthesization of this product to minimize the scalar multiplications. Do you know what the full parenthesization? You may not. You may know it, but you hear the term full parenthesization for the first time. It is this. So, in this case, n is 4. We are going to multiply 4 matrices, A1 through A4. And there are 3 multiplications. One is between A1 and A2. Another is between A2 and A3. And the other is between A3 and A4. And the full parenthesization, there are 5 distinct full parenthesizations, and they are enumerated here. And all of them are enumerated. And they are categorized line by line using some reason. What is it? 박종훈, 박근배, Okay. Can you find something common between the parenthesizations in the first line? 김범진. Yes, it is important. We categorized the parenthesization using the last multiplication. These two parenthesizations have something in common. What is it? In both parenthesizations, A1, the multiplication between A1 and A2 is the last multiplication. I'm not saying multiplying A1 and A2. I'm just saying that the multiplication between A1 and A2. Can you see the difference? In this case, this multiplication multiply A1 and A2. But in this case, this multiplication is done between A1 and the result of this parenthesis. Okay. And these are all parenthesizations where this multiplication is last. And how about this? In this case, the multiplication between A2 and A3 is the last one. And there is only one case. Finally, these two parenthesizations have this, the last multiplication. Can you see the symmetry between the first and the third lines? There is a symmetry. Okay? And now you see that there are only 5 distinct parenthesizations. Then let's think about the solution of matrix chain multiplication problem. First, let's think about a brute force approach. The brute force approach is like this. We enumerate all possible parenthesizations and then compute the number of scalar multiplications of each parenthesization. And finally, we select the parenthesization with the least number of scalar multiplications. Then what is the most time-consuming step among these 3 steps? 장영민. What is the most time-consuming step among these 3 steps? Especially the first one. Yes, it's true, but in this case, it's for each. So enumerating all possible parenthesizations takes a lot of time. It depends on the number of possible parenthesizations. And it's like this. This is the recurrence to find the number of parenthesizations. P of n denotes the number of parenthesizations when there are n matrices. And try to understand this recurrence. Yes, first, there are n minus 1 possibilities depending on the last multiplication. It is important. So, when the last multiplication is the first one, it means P1 by Pn minus k, n minus 1. That is this case. Then there are some possibilities to parenthesize this part. It is denoted by P of n minus 1. And P1 is the number of possible parenthesization of this. And when k is 2, it is this. N minus 2 and 2. So the k runs from 1 to n minus 1. So we enumerate every case. So if we solve this recurrence, we can find the number of enumerated parenthesizations. And it is like this. It is bounded below by, it is asymptotically bounded below by 4 to the n over n to the 3 over 2. Anyway, it's big. It's a large number. So I will not explain the detailed procedure. So we need a better method. It's dynamic programming. Let Mij is the minimum number of scalar multiplications for computing Ai through Aj. So this denotes, this entry stores the minimum number, the minimum special scalar multiplications to compute this. Then it is computed by this equation. Okay, look at this page and try to understand the meaning. So, in this case, we consider every k. K runs from I to j minus 1. That is, we consider every multiplication in this run. Okay, it's I and it's j. And then, this means when the multiplication between these two matrices is the last. Then the minimum number of multiplications of this run is stored in Mik. Okay? And this part, the minimum number of scalar multiplications of this part is stored in Mk plus 1 j, comma j. And then the last one, multiplying these two matrices. And let's see, this is I minus 1I. So Pi minus 1 by Pk matrix. And this is Pk by Pj matrix. Then to multiply this, we need Pi minus 1 K Pj. So it is this. And we have to consider every k between I and j minus 1 inclusive. Let's see an example. Okay, before we see this example, we know that the dynamic programming is a bottom-up approach. Then we have to define what is bottom and what is top. In the assembly line scheduling problem case, the first column is the bottom and the last column is the top. Do you remember? But in this case, we have to define it first. What is the bottom and what is the top? Think it over for a couple of minutes. Yes, perfect. Look at this recurrence. To compute mi comma j, we need to know ik and mk plus 1 comma j in advance. So these values should be computed before we compute this. So, and what's the meaning? What's the difference? The interval length of these two values is smaller than this. This is the interval of j minus I plus 1. And this is shorter. So, the one length interval is the shortest. It's the bottom. Then 2 length, 3 length, 4 length. So we compute those values step by step like this. So look at this. This is m1 comma 1 and 2 comma 2, 3 comma 3. So this is the bottom. One length interval. It means only one matrix. So we don't require any scalar multiplications. So they are initially zeros. And then from this value, we compute this is a level 0 and this is a level 1. All 2 length intervals. And all length 3 intervals. 1, 3, 2, 4, 3, 5, 4, 6 in this way. And then all lengths 4 intervals. And let me show you how to compute this interval, m2, 5, m2 comma 5. And it is explained here. Look at this part carefully for a moment. Then I will explain. We are going to compute m2 comma 5. So there are 3 possibilities of last multiplication between 2 and 3 and 3 and 4 and 4 and 5. There are 3 possibilities. So we calculate every possibility and then take the minimum. So these are 3 possibilities, and by using the already computed table, we can get 0 and 2500 and this. So it is 15,000. Similarly, we can compute the values. So we enumerated all the values. Then what is the minimum? This is the smallest one. So we store it in the entry. And we maintain another table S, and we store 3 here. S2, 5, we store 3. What's the meaning of this like? So this means we store which one of these is the minimum. So later we have to trace back. Do you remember the assembly line scheduling problem? We maintain the array L to trace back. So in this case, this table M only shows the minimum number of scalar multiplications. So if we want to find the minimum parenthesizations, we have to trace back. To trace back, we have to store that this case is the minimum of these 3 cases. That is, K is stored here. The minimum K, 3, is stored here. That's this. So similarly, we can compute all the other values. Okay, then questions. Why the lower triangle? Why is this lower triangle empty? It's undefined. If J is smaller than I, the matrix chain multiplication problem is not defined. So that's why the lower triangle is empty. The matrix chain multiplication problem is multiplying all matrices from AI through AJ. So if J is smaller than I, it is not defined. So it's empty. Then let's think about the running time. Okay, before we think of the running time, let's think of the space consumption. This is an n by n matrix. So the space consumption of this algorithm is theta of what? N squared. Because we store about n squared over 2 elements. Okay, and we have another table. So the space consumption is n squared. Then what is the running time of this algorithm? Emma? N squared? Just n squared? Can you explain why?
Because you have to calculate all the spaces. And when
So, I mean, the number of entries is theta of n squared. But then, think about it. What is the time to compute an entry? To compute an m I comma j. How many times are required to compute this? The hint is given here. Look at this. To compute an entry, the k runs from I through j. So it is theta j minus I, it takes theta j minus I time to compute this. What is the worst case? When j is n and I is 1. It is theta of 1, theta of n. So it is theta of n cubed in total. In the worst case. So the running time is big O of n cubed. And I showed that the worst case is theta of n cubed. Okay, we have to think of the best case. But by a careful analysis, you will find out that it is also theta of n squared, n cubed. But it's quite tedious, so I'll skip it. That's why I used big O here. It is safe if I use big O. Okay, and I explained the space consumption. And then I'll ask you a question like this. Do you remember that we could reduce the table F in the assembly line scheduling case? Do you remember? When we compute the stations in column I, then we use only the values in the column I minus 1. So we don't care the previous values, so we use only 4 entries in the assembly line scheduling case. I ask you the same question. Is it possible to reduce the table M in this case? Yes, the K starts from I to J. When K is I, we access the length 1 entry. So if it is possible, we should use only I minus 1 length intervals to compute a length I interval. But it is not true in this case. We access every level, so we cannot reduce the table M. And yes, that's it. Okay, do you have any questions about this? Space consumption? Look at this table. This is an n by n matrix. So, and we use the half of the table. So we need n squared entries. N squared entries. Ah, why? Okay. To compute this entry, we access level 1 values, level 0 values, level 1 values, level 2 values. We access all the values. So we cannot exclude lower level values. Okay? Any more questions? Okay, then after this class, feel free to ask me more questions personally. Okay, well, see you Friday.